We are going to start with some very general comments about linear regression. Later, we're going to discuss multiple regression, which is not that big of a jump beyond it. And then we're going to turn to some Excel and see how we can implement regression in Excel pretty easily, right? So fundamentally, simple linear regression, all it's doing is finding a linear relationship between one independent variable and one dependent variable. And so you could already think about that stuff that we were discussing in terms of trend lines. That's regression, right? That was very simple linear regression. And again, we've got this method for building both mathematical and statistical models that talk about the relationship between variables, right? And so it's good if those two things are connected to each other. And what I mean by that is with mathematical models, those are oftentimes theoretical, where we can think about the reason why one variable may have an impact on other variables. And we could think about some reasons that could explain how variables are related to each other. But we also want to have statistical models where we're actually looking at data to investigate what the data says the relationship between variables are. And oftentimes, right, we want those things to work in concert with each other so that we can not just try to think about what we think the right relationship between variables are, but we could look at data to figure out what the right relationship is. And by looking at the relationship that we could uncover in data, that might tell us something about some underlying causal relationships. And so it's nice when there's this concert between these two things. It doesn't always happen, but that's when it's the best, right? And so to help think about this, I've pulled out, there's some data that we're going to look at that looks at the market value of a house. And so I'm assuming that everyone understands what that is, right? But basically, what's a house worth? And we also have, horizontally, what we're measuring is the amount of square feet. And so the first question I could ask is, in this construction that we've made, what is the dependent variable and what is the independent variable? And again, you can think about the way that we usually describe those things. Usually, the variable that we're measuring vertically is the dependent variable, and the variable we're measuring horizontally is the independent variable. And usually we think of that as having a causal link. And so think about, is there a causal link between the thing we're measuring horizontally and the thing that we're measuring vertically? Do changes in the size of the square feet of a house influence the market value? Think about whether or not that causal relationship, that mathematical causal relationship that we just set up with our words makes sense. Could we have the reverse causal relationship also work? Could we have the amount of market value influence how many square feet a house is going to be? Think about whether or not that reverse causality might make sense, right? Regression, though, we're going to start a little bit more broadly with regression. What we're doing with regression fundamentally is, if we have some data, what we're doing is we are trying to find the line of best fit. And so we're gonna figure out what a line of, and again, a linear regression is just a linear line of best fit. And so most of our simple linear regression is just going to be a straight line that best captures the data. In a few seconds, we can more formally describe what it means to find the quote-unquote line of best fit. Formally, it's going to be finding what we call least squares regression. We want to mention two different types of regression, though, right? And so this gets back to the idea of, do you remember the difference between a population and a sample, right? And we had some different notation for those two. When we were talking about the population mean, we were talking about mu, and oftentimes we're not really going to ever be able to observe the population average, but rather what we can do is we can pull out a sample from that population, and we can calculate an x-bar from that sample. And hopefully, if things are representative, that sample average is a reflection of the underlying population average, right? But oftentimes we're not going to be able to observe that true underlying population average. Similarly, we want to talk about two different types of regression. The population regression is the true underlying relationship between x and y, between my two variables x and y. And so the population regression is made up of a couple of true underlying population parameters, right? So notice with my terminology, I'm calling x and y variables. I'm calling beta naught and beta 1 parameters, right? My variables are x and y, my parameters are beta naught and beta 1. Oftentimes, just like the population parameter of mu, we're not actually going to be able to observe what beta naught and beta 1 truly are. But think about if we had if our x and y represented the story that we had over here, where y was representing the market value of a house and x was representing the amount of square feet in a house. Can you describe in words what beta naught would represent? Can you describe in words what beta 1 would represent for this underlying population relationship of x and y? But again, remember, we're talking about a population relationship here. So it is the true underlying relationship between these variables, which oftentimes we're not going to be able to observe, right? But that's what beta naught and beta 1 would be describing, right? They'd be talking about the relationship between square feet and the market value of a house, the true underlying population relationship between those variables. Notice none of our models are ever going to be perfect, right? And we can just glance at this data and see the data isn't perfect, but also theoretically there's no reason to think that the amount of square feet is going to perfectly describe the market value of a house. There are other things other than square feet that influence market value. That's what this error term EI represents. EI represents the amount of stuff that influence market value other than what's in our model, in this case, square feet. These are things, the error term are things other than how big a house is that could influence what the market value is. And so another question I could ask is, can you give me some example of some things other than how big a house is that could influence the market value of that house? Right, and so then we've established what we think, theoretically, the relationship between these variables are with the population regression. Then what we'd want to do is then we'd actually want to turn and look at data. And when we actually turn and look at data, then we're talking about an estimated regression. That's looking at a sample of the population, right? If we're, in this case, a sample of house values. This is not all house values, this is just a sample of house values, right? And so from that sample of house values and the sample of square feet, we could come up with our estimated relationship between the variables, right? And so notice when we've got the estimated story, we change our notation a little bit, right? So the estimated left-hand variable, I'm calling that y hat, right? Or alternatively, I could refer to that in this context as the market value hat. Whenever we put a hat over a variable, what we're saying is this is the estimated value. It's not the actual value, it's the estimated value of what the house is worth. And notice that my betas now became, in this version, lowercase b's, right? So lowercase b naught and lowercase b1. Sometimes in other sources you might see beta naught hat, beta 1 hat. And so again, the difference is without the hats, those are the true underlying population values that we probably will not ever be able to observe. What beta naught hat, beta 1 hat are these are the estimated values of the coefficients, or of the constant and the parameter on the coefficient of the x, in this case, square feet, right? So again, hats, estimated values. No hats, true underlying population values, which we can't actually observe, right? So that's some very, very big pictures in terms of explaining what things are. Now we've got an additional way that we can describe what the line of best fit is. In order to do that, notice that in our estimated regression, this term dropped out. It's actually still there, we just don't write it. So one of the things that we do when we come up with our line of best fit, when we estimate a regression, is that error term, right? And remember, that error term represented all the things other than square feet that influenced market value of a house. What we assume about that error term is that on average, the error is equal to 0. We assume on average that the error term is equal to 0. So what's the estimated error term? It's 0, right? So, but we don't ever write a 0. We don't want to write plus 0. So instead, we just suppress writing it, but we know that implicitly it's there It's just equal to a value of 0. We can more formally define not the average error, but an individual error, EI, is equal to yi minus y hat I. Remember, we've got to introduce some we've introduced a little bit of notation that we want to come back to. What yi represents is the actual observed value of y. Right? So it's the actual observed value of, in this case, a house. This is what a house was actually worth. This is the actual observed value, and y hat is the estimated. Right? According to our little model, it's what the model estimates the value of y should be. It's the estimated value of what the house market value should be based on an amount of square feet. What the error is then, the EI for an individual observation, is then just the difference between what the house is actually worth and what the model says it should be worth, right? And so again, boy, this sounds familiar, right? Can you think about all the things that might represent the difference between what a house is actually worth and what it's estimated to be worth? Here we go. Step back a second. If your error term is positive, does that mean that your house is worth more or less than what the model predicts? And then we can also say, right, what if you have an error that's negative, right? What does that mean about whether your house is above or below what the model of square feet predicts it should be, what it should be based on its size? Notice, right, we've got this graphic up here that we're going to turn to in a second in Excel, but if I do a line of best fit, notice that there are going to be some houses who are above average and some houses that are below average, right? But on average, all of the errors average out to be about 0, right? Fundamentally, that is what the line of best fit does, right? So if I've got a bunch of data, there are two pieces of information that I can control. I'm going to do this with a nice little straight line, right? Two things that I can control. One thing I can control is where the line starts. I can control this vertical intercept, and I can also control the slope. So I can draw many different lines. Here, let's add a different line, and we'll do it as a different color, and I'll kind of point out why this is a ridiculously bad line. That line in orange, is that a line of best fit? Right? Yeah, it's a line. It fits the data. It's just not a very good fit, right? But again, for that line in orange, I could control the vertical intercept and the slope. I made the vertical intercept a little bit higher and the slope a little bit flatter. And I'm going to assert that that line in orange doesn't do nearly as good of a job of capturing what's going on in the data as my initial one in black. One way that I can formalize what my gut tells me about those two lines is I can think about, for each of the different observations, for each of the different data points there, I could calculate how far away that point was from the line. For each of those points, I could calculate how far they are from the line. And that distance down to the line is the error. If I calculated the error for the line in black for each of the points, and then I took all of those errors and I squared them and added them all up, I would get a number. And that number is what we call the sum of the square of the error terms. The error sum of squares. That's equal to, for a line of best fit, the value from each of the points down to that line, that error squared. And if I total all them up, that's my sum of the error squared. But think for a second, right? I'm going to change this to orange as well. If I have my line in orange, this point that's right over here, that error term is much larger. It's all positive on all of these error terms, right? If I took for each of those points and I drew a line down to that line of best fit on the orange line, all those errors, if I took them and squared them and then added them all up, I'm going to get a much, much, much larger value, right? And in fact, what regression does is it tries every single combination of vertical intercept and slope until it minimizes the error sum of squares. It's going to control the vertical intercept and the slope in a way such that it minimizes the error sum of squares. How does it do it? Okay, so we can very briefly go off on a tangent on how it does it. Again, two different parameters that we can control: the vertical intercept, the beta naught, and the slope, the beta 1. I'm actually going to start with the slope. The way that regression works is it does this god-awful looking calculation. I actually hate this version of the formula. There are other versions that I think are a little bit more intuitive. But what it does is we've got some x values, in this case square feet, and it's got some y values, in this case market values, and it carries out this long calculation. It's the sum of the square feet times the market value minus number of observations times the average square feet times the average market value divided by the sum of the square feet squared minus the n times the number of average square feet squared. That means nothing, right? Pause real quick. I'm going to pull up a different version of this equation. So this is not in your book, but I want to spend just a few minutes talking through the intuition of this equivalent version of how we estimate the slope in a line of best fit. This one has some things that we've seen before, and so that's why I think it's a little bit more intuitive. It's got, again, you got a numerator and you got a denominator. In your numerator, what are you doing? Same thing as what you're doing over here. It's just, this is a different way to write that out. You're multiplying two different things together. You're adding up a bunch of things. You're adding up a bunch of products. And this first term, what do you have? You've got your x value minus x bar. Right? So what we're doing is we're taking each value of the x's, in this case the square feet, and we're subtracting the average, in this case average square feet. This term, we've seen this before, this is called a mean deviated term, right? Where what we're doing is we're looking at the value of the x's that are mean deviated. If this value is positive, then it's saying that that value of x is above the average. If this mean deviated value is negative, it means that that value of x was below the average value of x, right? So what we're doing is we're taking the mean deviated value of x and we're multiplying it by the mean deviated value of y, right? If this mean deviated value of y is positive, it's saying that we've got a house value that's above average. If it's negative, it means that we have a house value that's below average. All that we're doing is we're taking, for each of those points, figuring out is it's mean deviated square feet times the mean deviated amount of market value. I blanked on what it was for a second. So real quick, if we looked at this data up above, and I'm actually going to pause and make that a little bit bigger for this story. We've got it a little bit bigger. Let's go ahead and let's take the x's and have those be in green, right? So if I'm looking at the mean deviated value of x's, I got to first figure out what's the average square feet, the thing I'm measuring x. Maybe it's about right here. So if I do a little, notice that each of those points that are to the right there represent above average x. Each of the points to the left represent below average x. So you can think about what the mean deviated values of those are. For the y's, the market value, let's do those in red, right? So again, the average market value, looks like it's somewhere around here or so, right? This is, if I wanted to label that, average market value, or this is the average y, right? Notice that everything that's above is above average, so its mean deviated values are positive. So here we go. What are we doing? We are summing up. We're adding up the cross product of all of these mean deviated values, right? So what we're doing is, look down here in this upper quadrant, this upper right quadrant, we've got positive x mean deviated values, positive y mean deviated values. So all of those are going to have a product that's positive. We're going to be adding all those positive numbers to all of these values that are in this upper left-hand quadrant. We actually don't have that many, right? But notice that they are positive y mean deviated values, but negative x mean deviated values. So the cross product of a positive and a negative, all of these are going to be negative, but there's not too many. Notice that in this bottom right, it's also going to be opposite signs, but there's almost no observations that are down there. Most of our observations are down here in this bottom left quadrant, where we've got below average y and below average y and below average x. I was pointing the wrong direction, right? So we've got a whole bunch of observations that are all positive, because we've got a bunch of negative times positive mean deviated values. So if we add all of those up, it's going to give us a value, an aggregate amount that's a positive number, right? And not surprisingly, you have positive slope. My numerator, whether this product is a positive number or a negative number, is going to tell us whether it's an upward or downward sloping. The denominator is never going to determine that. Why not? Because what do we have in our denominator? In our denominator, all we're taking is the mean deviated value of x, and we're squaring it, right? Because we're squaring it, this denominator is never going to be negative, right? But think about what this denominator is. Have you ever seen anything like this before? We've got the variable minus its average squared. Does that sound familiar? We add up the mean deviated value squared. My goodness, wait for a second. What if I did this? Does that does that formula look familiar to it? Hopefully this should look very, very familiar. Doesn't that look really similar to the variance, right? In general, that's what we're doing in our denominator, is we're talking about how much variability we have in our x's. The numerator is really the big driver of this story. It's about, is that variability in x associated with the same mean deviated value of y or the opposite mean deviated value of y? It looks like it's associated more with the same mean deviated values because we're in this upper right and bottom left. That's where we have the same mean deviated values, and that's going to produce a positive value, which produces a positive slope. So that said, all of that said, don't worry, I am never ever going to make you do any of this calculation by hand. Instead, we've got statistical software that can do that. Excel is going to do that. I just wanted to spend just a few minutes talking through the intuition of it. And notice, I was telling my story entirely in terms of the slope. Once I know what that slope is, it becomes the way that we calculate the vertical intercept, which is just the slope of the average x from the average y. That gives you what that coefficient is. But again, we don't have to worry about this. Excel is going to carry out this calculation for us. So let's turn to Excel. Notice that we've got our data set that we're looking at is also up on Moodle called Home Market Value. We've got a couple of different variables here. So again, we can ask the question, is this cross-sectional, time series, or panel data? And so notice we've got a bunch of different observations. What's our unit of analysis here? What do each of these lines represent? They represent an observation that is a different house, right? So this is house level observation. We've got the house's age, we've got square feet, and we've got market value. Do you remember the model that we were estimating, right? This has 3 variables, but we were only doing a model that had 2 of them. Real quick, can you recreate that graphic that we had before, right? So we were looking at square feet and market value. So if we highlight all the data and we insert a little scatter plot, right? Our scatter plot, again, horizontally, that's the first variable that we highlighted, square feet. Vertically, the second variable that was highlighted, in this case market value, we had this. And we can jump straight to this, right? If we just went ahead and did a trend line to this, and I need to bring it up, the options, so that I can add the equation. Here's my equation. And we could also do, here's my r squared. That's one way that we could estimate regression. But we might want to know a little bit more details. And so how can we carry out the full regression in Excel rather than just bringing up the estimated regression in a trend line? That's what we're going to do. But this is the picture that we're telling, right? So you do not have to highlight the data first, but rather under the Data tab, Data Analysis, you should have that because doing an add-ins earlier, right? There's an option called Regression. Go ahead and select that, and it brings up a dialog box. This dialog box has a couple of different pieces to it that we want to talk through. Number one, we've got the Y range and the X range, right? So the Y range is really the variable that you have on your left-hand side. What was the variable that we had on our left-hand side, right? It was the one that we were describing as if it were the dependent variable. That was market value. So I'm going to go ahead and I'm going to select the cell that has the label in it and highlight all that data. And when I do that, right, I start in C3. So I'm going to remind myself to go ahead and select the label to begin with. That's helpful, right? Because if you don't select the label, or if you don't highlight the label when you input the data, it's just going to call it variable 1, variable 2, and it's a little tough to keep track of things when you've got many variables. Your X range represents the variables plural, that you had on the right-hand side. But notice for this first model, we were just doing simple linear regression where we had a single variable on the right hand of square feet. That's where we're going to start. When we go to multiple regression, all we're really doing is just adding more variables to the right-hand side. So all the X range would do would just be highlighting all the X's that we want on the right-hand side. But we're starting with just square feet. It starts at B3 and it goes all the way down to B45. Notice that the X range and the Y range, that these two ranges, they have to match, meaning they have to have the same number of, not observations, but the same number of rows, right? And so it looks like 3, 45, that's a difference of 42, 3, 45, that has to be a difference of 42. They don't have to match up, they just have to have the same amount, and it's doing a relative calculation. We skip everything else for right now. Where do we want to put the regression estimates? That's what the output is. Where do we want to put it? You can either put it in a new worksheet ply, or alternatively, you can put it right in your data. So let's go ahead and put it in, say, let's do E3 so that it's right next door to all of our data. Let's put it in E3 and go ahead and click OK. And notice in E3, it started generating all of our regression output. So it's got different sizes, but there's some different things that we want to talk through. Notice right away, some of these numbers fit what we had when we did the basic trend line story. We had an R-squared of 0.5347. Can you find that number anywhere in this mess of output? Sure you can, right? It's one of the important pieces of information is R-squared. So go ahead and make note of that. When we estimate regression in Excel, that's one thing that your eyes should very quickly be drawn to. It's one way to talk about overall how well our model is describing the data, right? We're going to more formally define what it represents in half a second, but it is one place where your eyes should instantly start, right? And again, what are the ranges of R-squared? What's the lowest value you could observe? What's the highest value you could observe? The lowest value of the R-squared is 0. The highest value is 1. So this is a number that's somewhere in between the two, right? But we can talk about what the R-squared of 0 or the R-squared of 1 would look like in a few seconds. Notice there's one right below it called the adjusted R-squared. This matters when you have larger models. Right now, our model is not that big. What do I mean by big or small models? I mean, how many variables do we have on the right-hand side? We only have one variable on the right-hand side. We don't have that large of a model. But if we had 4 or 5 variables on the right-hand side, then we've got a bigger model. And so we've got some concerns with just arbitrarily adding more variables to our model to make it bigger. It's always going to be capturing more and more. You remember that polynomial trend line? We had a whole bunch of variables on the right-hand side. And so our R-squared was going up. Our adjusted R-squared takes into account the size of the model. We're going to come into that a little bit later. Number of observations, not surprisingly, it's 42, and that should be a number that jumps out from what we just went through. What else? In this second section, the ANOVA section is what we want to talk about first. The main thing that your eyes should go to is this significance F-test. This significance F-test is that a very big number or a very small number? Right? This is a very, very small number, 3.798 e to the negative, that negative is important, negative 0.8, right? And so that's a very, very, very small decimal. That value is actually a p-value. Pause for a second. I want to go back and talk about what it's a p-value associated with. This is the last time that we saw ANOVA, was in statistical inference, right? That ANOVA in regression is asking a similar hypothesis test, but instead about asking, do we have any of the averages being different from each other, instead, what this is asking about is the betas, right? Are any of the betas, or the null hypothesis in that is, are any of the betas equal to 0, or are at least one beta not 0. Basically, what the ANOVA in regression is asking is anything in your model not 0, right? The default null hypothesis is going to be that everything in your model is 0. And think about it for a second. If we've got a model of market value as a function of, that's a beta 1 or beta naught, of square feet, if everything is 0, then square feet has no impact whatsoever on market value. If anything is not 0, it means there is some kind of relationship between square feet, between any of our variables. And again, remember, with the analysis of variance, this is not a normal distribution. Rather, it's an F distribution, which looks not quite normal. But the same basic logic of do not reject, DNR, do not reject, and your rejection region fit. Do you recall, what was the p-value that we just came up with? The p-value that we came up with was an amazingly small number, right? So we are way below an alpha of 0.05 with that very small p-value that we found in Excel, meaning we reject the null, meaning we believe our model is telling us there's some kind of relationship between these variables. That hopped back a little bit to a previous topic, but again, your eyes should be drawn right here, and this is the p-value associated with an ANOVA test of is anything in your model not 0. This number is, for most of the time, going to be not something to worry about. Glance at it, right? Again, R squared, your eyes should definitely go here first, and then glance down here, and almost more than likely, this thing is going to be statistically significant. And again, by statistically significant, what I mean is it is this is a p-value, and that p-value is going to be lower than a lot of the traditional level of significances that we care about, right? The 0.05, the 0.10, the 0.01. This becomes more important later on when we have larger models. I actually want to glance here, and then I want to spend the rest of my time focused on some of these other numbers, right? So if you recall, our very simple model was your market value as a function of a single variable, square feet. I've got 3 different names in this first column: regression, residual, and total. Next to it, I've got degrees of freedom, right? So degrees of freedom are related to some of the things that we were discussing earlier, right? When we were talking about the t distribution, when we were talking about inference and those sorts of things, right? It's related to that, but it's a little bit different. Here we go. Here's how we come up with these numbers. The total degrees of freedom in this ANOVA is the number of observations minus 1. So we had number of observations n 42 minus 1. That's where the 41 comes before. The total degrees of freedom are n minus 1. The regression degrees of freedom are equal to the number of variables on the right-hand side of the equation. In this case, we only had one variable on the right-hand side of the equation. We refer to that as actually k, right? So k is the variable, or is the notation that we use to describe the number of variables on the right-hand side. The degrees of freedom of regression is the number of variables on the right-hand side. The total degrees of freedom is n minus 1, where n is the number of observations, that we have in our data set minus the number of minus 1. So what do we got? Total 41, which was 42 minus 1. Regression was 1 because you had one variable on the left-hand side. Residual, right? When you think about the word residual, what does that mean to you, right? Residual is usually what's left over. Yep, here it is, literally what's left over. So the residual degrees of freedom are the total degrees of freedom minus the regression degrees of freedom. So the residual degrees of freedom is going to be a messy equation that's what? N minus 1 minus k? Yeah. That's how we get that. That's a messy way to do it, but it works. Degrees of freedom are one thing. It's not that big of a deal. Our main focus right now, I want to turn and I want to talk about the SS. SS for sum of squares. We've already used that term, right? We have 3 different sum of squares. We have a total sum of squares, we have a regression sum of squares, and we have a residual sum of squares. It's a little bit complicated. I want to hop back and look at a picture to help figure out where these come from. But before we do that, I want to point out one little thing about that. Oh, I've got the big numbers here. I want to point out one little thing, right? When I have my total sum of squares, if I subtract out my regression sum of squares, I'm left with my residual sum of squares. Notice, what was left over when I took my total minus my regression was my residual. Or alternatively, my regression plus my residual is equal to my total, right? My total is equal to my regression plus my residual. I'm going to go back to that picture and try to talk about where those values come from. I want to start out with the total sum of squares, because I think that's a natural place to start. The total sum of squares is equal to the sum of all of your y's subtracted from the y bar. Add them all up, right? Hey, this is something we've seen before. This is a mean deviated value, right? This is the mean deviated sum of squares. What are we doing here, right? So if I look at a bunch of data, all of my different observations, if I tried to think about where the average value of all those y's were, I marked it as right here, right? This is the average y. What this right-hand side of the equation is doing, we're going to consider this little point right here. If I look at the distance, the difference between that point and the overall average of my y's, that overall average of the overall average minus the individual observed value, that is yi minus y hat. And that's what I'd refer to as, if I summed all those up for each of the different points, that would be my total sum of squares, right? In black, that's the total distance from a single observation and the overall average of the y's. Let's hop down to the bottom one, because I think this is actually the next natural progression to think about. The residual sum of squares. Hey, we've talked about the residual sum of squares, right? If we know what an actual observed value was, and we subtract out what the model estimated the value would be, that's the error, right? So here we go on this graphic. This dot right here was the actual observed value, right? The yi is the observed value. In this case, observed for a house value. But given how big it was, given what the value of x was, given what the square foot was, the model, the line of best fit, predicted or it estimated that this would be the value, right? If you recall, right, y hat, that is, y hat is the estimated value, right? And the difference between the observed and the estimated value, that is what we call the error sum of squares. Or that would be the error, and if we totaled them up for all the different points, that would be the error sum of squares. Now we turn to the remaining piece. The remaining piece is the regression sum of squares, which we already said is the difference between the total and the residual. Notice how it's made up though, right? This is a really not a straightforward intuitive formula, right? So far, notice what have we used? In our total sum of squares, we used the observed value and the overall average value. In the residual sum of squares or the error sum of squares, we were using the observed value and the estimated value, right? We've got one combination of y's that we haven't used yet. It's a little counterintuitive though, or not counterintuitive, but it's not necessarily intuitive to begin with, right? We're using the overall estimated y, or the overall estimated average y, and the estimated value of what y should be based on the model. This is such a strange thing to put into words, right? But what the regression sum of squares looks at, right? So it looks at what was, again, the overall y, average y. And it looks at the difference between the average y and what the model predicted the value of y should be based on a model of X. It looked at the estimated value of Y. The difference between the estimated value of Y and the overall average of Y is what we refer to as the regression part. And in this case, if we total them up for all the different values, it'd be the regression sum of squares. So you may want to go back, I paused it and then reset it so it wouldn't get too messy at a single time, but you might want to go back and make sure you understand each of those different pieces. But again, what we're arguing and what we saw with regression, when our regression in Excel, was the total sum of squares, which looks a whole lot like something related to variation, right? It's kind of like the variation in X. We just have a different denominator, right? But that total sum of squares tells us the total, not variation in X, sorry, the variation in Y, right? It looks like the amount of variation in Y is composed of these two different pieces in regression. There's this portion that's related to what we're the regression piece, and then there's this portion that's unrelated to the model. This error piece, which is what's left over from our regression. The total amount of variation in our Y is made up of variation that's captured by our regression as well as leftover variation. Yeah? I am back to Excel to do one quick thing here, right? So again, total sum of squares. That's the total amount of variation in the thing I'm measuring vertically, in this case market value, right? It's not variation because I'm not dividing by 1 over n, but it's going to get bigger if I have more variation, right? It's made up of these two different pieces. There's the regression sum of squares, which is, as we just talked through, it's related to the variation that's being captured by the regression, and then there's the residual sum of squares, or the error sum of squares. That's what's left over. Real quick, if I do a calculation, I can take the regression sum of squares, I can take the regression sum of squares, or the variation that's being captured by the regression, and if I divide that by the total sum of squares, I get a number that should look familiar to you. Where have you seen that number before? That is exactly what the R squared is. All of that leads up to our new conclusion about how we actually interpret what the R squared looks like, right? We can talk about it in general, right? It tells us how well the trend line fits the data. That's too general for us. From now on, we've got a much more precise way of describing what the R squared is. The R squared is actually a measure of a percent, right? The R squared is actually measuring a percent value. It's specifically telling us what percent of the variation in the thing we're measuring vertically is being captured by our regression model. 53.47% of the variation in market value is captured by the variation in square feet. Seen differently, right? The total sum of squares is the total amount of variation in market value, how much spread there is in market value, and what the R squared captures is what percent of that variation is being captured by our model. And in our case, our model was a model of square feet. 53% of the overall variation in the market value of a house is captured by looking just at the variation in square feet. Notice, if we do 1 minus the R squared, what are we getting? We're getting about 47%. That also means that 47% of the variation in market value is explained by something other than what's in our model, right? That's what the residual or the error sum of squares is capturing. How much of the variation is not being captured in the model, right? What I want to do is I want to draw a couple of other, I'm going to pause and put in a couple of extra pictures here that show different R squared values. And then we'll talk about it in this context of total sum of squares, residual, and regression sum of squares. Okay, so I've got two different presentations of data there. Let's just real quick think about what the average value of y would be, right? In the upper right-hand one, maybe that's the average y. In the bottom left, maybe that's the average value of y, right? And you can think about how spread out the y is. There's this total variation, right? And so let's pick a point. There's the total variation. That's the difference between our overall y bar and the observed y bar. And let's pick this point here. Observed y and the overall y. Can you think about what the line of best fit would be? Oh my goodness, right? So let's try to add a line of best fit to the bottom left. That's an easy one, right? The line of best fit is probably going to look something like this. And so this is the point, right? That if I do my line of best fit here, and then I try to add on the regression and the error sum of squares, where would that look on this graph? The regression sum of squares is the one that I was doing in green. That's I got to look at for that value of x associated with this. Where does the line of best fit predict or estimate the value of y what it should be? Boy, it looks like it's just barely below that one, right? So again, in black I've got my total sum of squares, and in green that's going to be my regression sum of squares, which means in red that distance between the two, that's my error sum of squares, that's going to be really small, right? It looks like in black almost all of that variation is being captured by this regression model. And not surprisingly, if you step back, you probably remember this from earlier Stats 1 class, this is going to have an R squared that's really high, maybe like 0.98 or something like that. I mean, that's a really all that data looks very close to the line, right? Upper right hand, this is going to be a little bit more awkward, right? But so if I've got in black, if that's what the actual average is, boy, if I try to add again in purple a line of best fit, oh gosh, I don't even know. Where is the line of best fit on this? It's maybe this, maybe that's not. I don't know where the line of best fit is, but it's a really flat line. It's not much of anything whatsoever. So that again, if I try to fill in my pieces, right, that line of best fit predicts that for this point, it's going to be somewhere around here, right? That's how much the regression sum of squares, and there's just a huge portion between this line of best fit that's very flat, all the way up to what that point actually is. Most of the variation, most of the total sum of squares is actually being captured by the error sum of squares. Remember that another way that we can calculate the R squares, it's equal to the regression sum of squares divided by this total sum of squares. This number, this has an R squared of maybe 0.05 or something like that, right? Almost all of the variation in whatever I'm measuring vertically here is not being captured by the model. It's being driven by something else. So again, you probably remember seeing an R squared from an earlier class, but we wanted to do a little bit deeper dive into what it represents in this context. We wanted to hop back over to this, to the Excel work, and talk about some of the other things that are here. Oops, there's one other thing I realized I didn't do about the ANOVA. We've talked through where the regression, residual, and total degrees of freedom come from. We've talked about where the sum of squares for the regression, residual, and total come from. How about the next column? MS is for mean squared. Here we go. I'm going to make these columns just a little bit larger. I'm going to try to make these columns just a little bit larger. This mean squared for the regression, if I take the regression sum of squares and divide it by the degrees of freedom, notice what I get. I get the same number. And if I do that for the line below. So again, check out what's being divided by what. If I take my residual sum of squares and divide it by the degrees of freedom for the residual, I get the mean squared. Doesn't have a whole lot of intuitive appeal to it, but it is what it is. Then the next column, the F value, is if I take the mean squared regression and divide it by the mean squared residual, I get the F value. And this F value, as we talked about before, is the statistic, the test statistic that we're using on that previously discussed null and alternative hypothesis that anything in your model is different from 0. And the column right next to it said, yep, that value of 45 was pretty far to the right of the distribution, so that the probability of committing a type 1 error, observing that and given that the null is correct, is very, very low. Again, none of that should be, it's important for you to be aware of generally, but it's not the first thing that your eyes should go through. The R squared, the significance F, just making sure that that's a low number so that your model is telling you something. That should be where your eyes go. The other place that your eyes should jump very quickly are to the coefficient estimates right here, right? So these coefficient estimates right here, I've got the first line is intercept, and the value is 32673. Does that one sound familiar? Sure it does. Look down to that trend line, 32673. That's the intercept. That's the constant term that we've been talking about, right? That's our estimate of beta naught. Right below it, 35.03. That is the slope estimate, right? And yeah, we talked about that with the trend line, what that represents, right? Formally, if we're talking about measuring market value as a function of square feet, can you put into words, what does that slope and intercept represent? If you were going to write this out, what's a good way to write it, right? So one of the things that you should start thinking about is deliberately, how many decimal places should you choose, right? So we've got for the intercept, the coefficient estimate of the intercept is 32,673.22. Do I need that 0.22? Is it essential? Or should I drop those decimals off? Alternatively, for square feet, I've got 35. But 35.06 or 35, drop them off, right? Or 35.036, right? So I think for a number, right, given that the overall number is just 35, that going 2 decimal places out, probably appropriate, right? You probably don't want to go 8 decimal places out because that implies a certain level of precision that probably is not there in the data. Right? The other thing that I wanted to do while we were here, because we are right next to the data, let's consider this very first house in the data set. What do we know about this house? It has 1,812 square feet, and it has a market value of 90,000. Is this market value of 90,000, are we looking at Y hat, Y bar, or just Y? What I'm really asking is this an observed value of market value? Is it the average market value in the data? Or is it the actual, is it the estimated market value, right? This is clearly what the actual house is worth, right? But can we calculate what the model would predict this house would be worth? Sure we can, right? And in fact, I wanted to be in Excel when I did this because I can very easily use some formulas, and then it's using many, many decimals, and this is going to be a very, very accurate piece of info, and I don't have to worry about rounding or anything like that. So I've got my intercept, which is my beta naught estimate, and I'm going to take the estimate of beta 1 of 3503, and if I multiply that by the actual number of square feet for this house, what I'm going to get from this formula is what the model predicts this house should be worth based on the amount of square feet. The model actually thinks it's going to be worth $96,159, but it was actually worth $90,000. What does that mean about the error term? Is it positive or negative? There's one other thing that I want to do while I'm here, right? So I've got the square feet market value and the estimated value. I want to paste these right here. I have to use my little the other one for that. I want to paste those values so that I have those exact values. Because I already had this formula set up, I want to change one thing. What if instead of having a house that was 1,812 square feet, what if instead it was 1,813 square feet? Right? If I've got 1,813 square feet, that formula automatically calculates the value that the model predicts. And why am I doing this? I'm doing this to do one thing, right? So that I can say, if I look at the difference between those two observations, or those two values, what I was doing was increasing the square foot by 1 unit, 1 more square foot. And this was the estimated market value. How much did the estimated market value change by? You've got an expectation of what this is going to be, right? Not surprisingly, 35.036, right? That's exactly what a coefficient is telling us. The coefficient tells us if we have 1 more unit in our independent variable, if we have 1 more square foot, it's how much market value is going to change by, $35. So I want to do one other thought process. What if instead of adding 1 square foot, what if we decided to add 200 square feet? So that would be what? 2012 would be the original 18 times that. If we added 200 square feet, is that surprising? Right? Again, if we just took an extra 200 feet and we multiplied it by the coefficient, we'd get the change in the market value. Think about why this information might be useful to you as a homeowner, right? If you were thinking about expanding your house, if you wanted to add a little addition to your house, the back of your house, not a very big one, say 200 square feet, should you add that square feet? It depends, right? It depends on what's it going to cost. What this did is this gave you an estimate of what the benefit is. This could tell you what's going to be the change to the market value of your house. It's going to be worth an extra $7,000 in the market value of your house. Now, what's it going to cost to put on that addition? And that might help inform your decision, right? So again, that's kind of how we use these coefficients in a way to help with decision making. To talk about this next part, I want to again remind you that there's a difference between the population and a sample, right? A population is the true underlying relationship between square feet and market value. But what we did is we weren't looking at the population. We were looking at a sample. And when we pulled out a sample, for that sample, we looked at the sample square feet and the sample market value. And when we plotted those out, we did our line of best fit, which estimated our value of our intercept and the value of the slope parameter, the value of the square foot coefficient. But what if we pulled out a different sample? If we pulled out a different sample, what would we get? And so that's what I want to do is my first sample was in black, but what if instead I pulled out a sample in green as follows? What if I randomly drew out a sample that looked like those green dots right there? If I took those green dots and I tried to do a line of best fit, maybe it would look a little bit different, right? Maybe it would look different in 2 ways. Number one, my intercept could be a little bit different, and 2, my slope could be a little bit different, right? So the point that I'm making is that the population is what we really care about, but we rarely ever actually observe that. Rather, what we observe is a sample. And what we talked about a few topics ago was when we pull out a sample, we're never going to get it quite perfect, right? There's going to be some uncertainty with this sample. And so maybe we've got some ways to talk about how our sample might look like what we think the underlying population is. In essence, that's what hypothesis testing was allowing us to do. And so when we get to hypothesis testing, we can ask hypothesis test about either the intercepts or, more importantly, I got a little normative there, the the coefficients on the slope estimates, the coefficient on that 35. So I'm going to go back to the Excel and talk about some of the pieces there that might be communicating the amount of uncertainty we have about those coefficients. Here we go. This right here, we've got our coefficient estimates. Right next to it, I've got a standard error. Right? Our standard error describes the spread of the variation that we think is in these coefficient estimates, right? So it's kind of like how spread out our x's are. If we're just looking at a bunch of x's, there's some natural variation in our x's. This is kind of like a measure of how much variation there is, but it's the variation in what we think the coefficient estimates are. Next to that, we've got a t-statistic. And you probably recall how to calculate a t-statistic, right? The way that we calculate a t-statistic is we take our estimated value minus what we think is true in our null hypothesis, divide it by the standard error. And so I want to real quick show you that back when we were doing the hypothesis testing, right? What did we assume was true in the null hypothesis? 0. So if I go back to my Excel, if I take my coefficient estimate and I subtract 0, I get the number. That's not very exciting. If I take my coefficient estimate, I subtract 0, which is what I assume in my null hypothesis, and divide by the standard error, I get the value of the t-statistic from up above. Right? So notice how I did that, right? The t-statistic is equal to the coefficient minus 0 divided by the standard error. The t-statistic, we can interpret it either for the intercept or for the coefficient on a variable. Notice, where does the 6.78 comes from? It comes from 35, which was our coefficient estimate. That's my beta 1 estimate. My 35 minus 0 divided by a measure of how spread out that coefficient estimate is, the standard error, right? Again, we can go back to what a t-distribution looks like and think about if I had a variable that, or a estimate that was 3.6, had a t-value of 3.6, or a t-value of 6.7, where would those appear on a t-distribution? If you recall, a t-distribution looks a whole lot like a normal distribution, right? It's centered around 0, and that's what we use in our null hypothesis. If we focus on the t-value and the t-statistic on the square feet of 6.78, where would that be on this picture? Remember from the empirical rule, if I go one standard error out for something that's going to be distributed normally, then that's going to capture 68% of the probability, right? Because of the central limit theorem, the distribution of our estimated parameters is also going to follow a normal distribution. So my goodness, right? If I go 2 standard errors, 3 standard errors, that's like 99, right? If I have to go 6 standard errors and it's positive, so it's 6 standard errors to the right, the amount of probability to the right of that point is going to be so small, right? If I use a traditional alpha of 0.05 for my level of significance, it's going to be somewhere around here, I am clearly going to be in the region where I'm what? Rejecting or not rejecting? Do not reject. I'm clearly going to be in the region where I'm rejecting the null hypothesis. Remember though, what was the null hypothesis? The null hypothesis is that your beta 1 is equal to 0. With this t-value being so high, we reject the null that this coefficient was 0. Think about this for a second though. If I've got market value, if my coefficient on square foot was 0, what is that saying? That's saying that when I increase the amount of square feet, it has no impact on market value. All right, so here's some double negatives, but this high t statistic is telling me that I reject that square feet has no impact on market value. This high T statistic is telling me the data suggests that square feet does have an impact on market value. And in fact, that impact is that for every 1 unit increase in square foot, the impact on market value is to increase it by 35, in this case, dollars. That impact of square feet on market value, it's not zero. The data tells me it's not zero. That's how I interpret the t-value. But notice, right next to it, you may like t-values to think about where they fall on a distribution, or you could alternatively look at a p-value. That p-value of 3.79 e to the negative 8, that's a very, very, very low p-value, right? Because that's saying that that t-value of 6.78 is so far to the right, there's such a small amount of probability to the left. Again, we can compare the p-value to the alpha value, and if p is less than the given alpha, we reject the null hypothesis. So, if we wanted to write out the estimated regression, this is a way that we could do that. If I wanted to write out the estimated regression, one way I could do it is by this, right? I've got my dependent variable was market value. My estimated intercept is 32673. And I probably don't need any decimals because of the size of that number, right? Is my intercept statistically significant? Well, it depends on what my level of significance is, right? But there's one thing that happens a lot when you see regression, right? So there are 3 main levels of significance that get reported a lot: alpha 0.10, alpha 0.05, alpha 0.01. If my level of significance was 0.10, is this p-value below it? Sure it is, right? Let's go to the next level, the more rigorous level of significance of 0.05. Is my p-value telling me it's still less than? Yep, so it's significant at a level of 0.05. Let's move on to a higher level of the highest level of significance, 0.01, right? The highest level of significance that's considered a lot of in a lot of the research, right? Yep, my p-value is even less than that, right? So one thing that happens is oftentimes, right, we use stars by our coefficient estimates to communicate what level of significance we observe in the data. Because that p-value is a very, very small number, it is below all 3 of those levels of significance. So we can do 3 stars to communicate that very succinctly, right? The number of stars would communicate what level of significance we have. Our intercept is statistically significant at the highest, the most rigorous level of significance of 0.01. What was the other part of it? It's got plus 35.03, and then the variable was square foot. And again, the p-value on that 35 is a very, very small number, so it's clearly would be rejecting the null hypothesis even if we used a level of significance of 0.01. So I used 3 stars to designate that. This is a simple way for me to summarize the estimated regression. I want to just very quickly talk through some of these assumptions that are built into hypothesis testing with regression, and then in later classes we can investigate these a little bit more formally. Number 1, linearity of the model, right? We can investigate. Is our model actually a linear model, or would other specifications of it look a little bit better? The other things that we can investigate, 3 of them, are all related to the error term. So again, we're going to tell this story about market value as a function of square foot, and we've got the error term, which is, again, for an individual house. It's what's special and unique about an individual house, other than how big it is, the things that influence its market value, right? If the error term is positive, it has market value that's above what the model actually predicts based on its size. If we looked at all of those error terms collectively, do they look like they're normally distributed, right? That's an important thing for us to have in order to carry out our hypothesis testing. And we could look at those. That's not going to be our main focus for this class, but we could. Homoscedasticity says is there the same spread of the error, right? So if we looked at two different sized houses, some houses that were 400 square feet and others that were 1,200 square feet, if we do a line of best fit, we'd expect the spread of our observations to be equal between those different levels of error, right? Is the spread, is the variation of the errors the same? But actually, you might think about, in real life, if you had a bunch of houses that are, and 400 square feet is an amazingly small house. I'm not sure why I came up with that number, but it's really small. I bet that for houses that are all this small, there's not a whole lot of variation in the market value. But if you've got a 1,200 square foot house or a 2,000 square foot house, 2,000 square feet, you can have some really bad 2,000 square feet houses. You can also have some really nice 2,000 square feet houses. My guess is that in real life, the spread of your actual number of houses for 2,000 square feet, the spread of the market value of those houses is actually going to be a lot bigger than for just 400, right? Homoscedasticity says, no, 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 no. The spread of the errors is the same for every value of X. It's something that we can investigate, and if we discover that we don't have homoscedasticity, then we have heteroscedasticity, and there are some simple things that we can do to our regression to try to adjust for that. Again, a little beyond this class, but I wanted to say out loud. Independence of the error. We also assume that the error of one house is unrelated to the error of a different house. Multicollinearity has to do with when we start adding more variables to the right-hand side. If instead of just looking at square feet, if instead we looked at the age of the house or other things, if there's an association between the square foot and the age of a house, then maybe that might make some of our estimates a little bit quirky. And again, in later classes we can investigate these things a little bit more, but we just wanted to mention them in passing here.